All right, so if we take a look now at surface water delta C13, these are measurements that we made on a shipboard transect from Ushuaia, Chile. So we ran up the coast of South America through the upwelling zone. You can see this is back in, God, I can't even remember. This is, I think we took this 2000.
Howie, just to not make the Argentinians mad in the room, Ushuaia is actually in Argentina.
I'm sorry. Thank you. Okay, I had the right country, wrong city. This happens where you have, all these people that do cruises out to Antarctica, and some leave from Ushuaia and stuff. It's Punta Arenas, so that's Chile, right? Okay, so my apologies to, this is probably like calling Montreal the U.S. Okay, so you can see the upwelling zone, and you actually start to pick up the delta C13 signal at about 20 south. And that's basically surface waters that are spreading out to the south. We have a maximum sitting at about 2 degrees south, or actually a minimum delta C13 at 2 degrees. And then as you come up out of this, once you hit about 1 degree north, you're out of the upwelling zone. Okay, so it's really tight on the northern side, and it's a gradual decrease on the southern. And the reason is because of the Humboldt current, because there is a lot of upwelling that's going on all on the coastline as you move to the as you move southward along the South American margin. So you're looking at this upwelling showing up in the delta C13 record, which is due to the Humboldt current. Okay, that's why it sort of tapers, whereas it's very, very sharp on the northern side. Okay, so I have a question to ask. Have you seen the pump handle video yet? Okay, the answer is no. All right, you would know if you've seen it. All right, so let's just now, I want to talk a little bit about about the CO2, atmospheric CO2 today, and what it's been looking like in the past, and the geochemistry of that carbon, and then we'll take a break. Okay, the atmospheric PCO2, as I said, should reflect the balance between oceanic upwelling and productivity. The ocean should be dominating, okay, what's going on, because there's 40,000 gigatons of carbon in the ocean, and there's only 700 gigatons of carbon in the atmosphere. The ocean's the big reservoir of carbon in the ocean. On timescales of hundreds of thousands of years, out to maybe 1 million years, okay, the carbon that's available to the terrestrial ecosystem, to the atmosphere, and to marine organics is locked up in this upper box right here. This deeper stuff where we have really most of the carbon that's on the planet, for instance, that's buried in reduced carbon, oil and gas, it's carbonates and carbon in the mantle, where we're talking now about hundreds of millions of gigatons of carbon, only play a role on really long time scales. Millions, tens of millions of years, where now you're getting into the fundamental subduction zone, upwelling, mid-ocean ridge type of processes that release the CO2. So we're really dealing only in this upper box. Obviously, CO2 has been rising. You've all seen this. Right? I don't have to belabor it. There's SIRFER 1. Who would have ever thought that when we started this course, okay, at 362 ppm, we would basically be up here looking at 412 ppm. Okay, that's what it was last month. All right. We are no longer below 400 at any time of the year. We had 401 during last summer, and from here on out, we're going up at a rapid rate. Okay, it's very scary. Why is it scary? Okay, so this is a great video if you haven't seen it. What we're looking at now is effectively the Mauna Loa curve, but we started here in 1980, and you're looking from the South Pole to the North Pole. And every one of those dots is a station that's collecting CO2. And what we're seeing on the right here is a cyclicity. Why is the CO2 cycling? Seasons, okay? All right, when it's high, which season? When it's high, which season? What? Okay, winter, which hemisphere? Northern hemisphere. That's northern hemisphere winter, that's northern hemisphere summer. So what you're looking at, and you can get a sense of what's been going on, of course, that a lot of the action's happening up in the northern hemisphere. Right, these big swings. The South Pole is just simply catching, it's integrating. what the atmosphere is doing. It's really well mixed in about a year. All right, and you're starting to see, you know, effectively, we're starting to get Asia coming online with all these big cold winters, and we're getting, what? Yeah, this, you can just download this off the NOAA website. But wait until it gets going. That's why I asked you about the pump handle. So we're watching Mauna Loa going, and we're moving up, so we're now in 2004. All right, the important thing to look at in this is the rate of rise, okay, and what's happening, okay, as you start to move. You notice we're having times in some of these stations where you're seeing 430, 440 ppm. Okay. All right, so eventually what's going to happen is we're going to, you know, today, as I said, where we're seeing already the summers at 411, so we're probably about over here for the modern. Okay, all right, so we've exceeded 400 ppm now. Now let's connect this to the planetary CO2 cycle that's occurred in the past. So if we now back this down, you'll watch the ages down here, okay, we're continuing on with the Mauna Loa curve going back to 1959, all right, give a sense of rise, all right. Now what we're going to do is we're going to connect this to the mountain glaciers, all right, as we move back from 1960, now we're going to move back, going back through the last millennium, and you'll notice that CO2 is pretty constant, and this is despite European deforestation, Roman deforestation. Not much is happening in CO2. And now let's put this in perspective with the ice core record. Okay, and now we're going to go back 800,000 years. And this gives you a sense of the natural variability in the CO2 system where we're bouncing from about 300 ppm to about 200 ppm, 190, going back in time. So now we're 50,000 years. Okay, and now we're going to go to the previous interglacial at 120,000 years, and CO2 is pretty close to where it was in the Holocene, okay? And our ice cores now go back about 800,000 years. And when you take a look at the long-term record going back, okay, across this 800,000 years, the first thing that obviously you should notice is that, number one, there's nothing like this, and the rate of change is unique during this period of time. You try to argue with somebody why this has to be human activity. You cannot argue, well, it's because it's never changed this quickly before. We've never seen numbers as high as this before. Come on, come on. Okay. Now, stick this on to the CO2 record that we've reconstructed for the last 50 million years. Okay, 60 million years since the age of the dinosaurs. And pretty much from the Pliocene into the Miocene, going back through the Oligocene, okay, through here, we're seeing CO2 levels that were bouncing between about 400 and 600 ppm. That's our estimates for the last 25 to 30 million years. And this comes from leaf stomata, it comes from organic geochemistry of lipids and waxes and things like that. Okay, and then once you get back to the Oligocene and into, this is now the Eocene over here, okay, we're seeing CO2 levels that are beginning to move upwards towards 1,000 ppm. All right, so in effect, our 400 ppm world, okay, is a world that we've seen before, okay? And not only have we seen it before, but during the Pliocene, the estimates are sea level was 10 to 15 meters higher than today. Okay, and that's just simply the loss of the West Antarctic ice sheet, a good part of East Antarctica, which the new models now can make East Antarctica melt, giving us sea level rises that we see here, and probably about 3 meters or thereabout out of Greenland. Yes?
What's the site 925?
Site 925, I believe this is the tropical Atlantic. I think that's Sierra Rise, if I'm not mistaken. Okay, and Sierra Rise is just sitting off Brazil. So you're looking at the Atlantic Ocean there. Okay. So you want to argue with, yes?
That's a really useful graph as it compares different methods to reconstruct climate.
Mm-hmm.
But is there a method to aggregate all of those into a most likely estimate?
Well, that's kind of, the answer is, you know, people don't want to do that right today. You know, there's a lot of the paleoclimate community has been hammered because of trying to simplify a perspective that has a lot of variability. So it's much better to show people where the variation is based on the different proxies, whether it's boron isotopes or whether it's leaf stomata or whether it's carbon isotope geochemistry of organic matter, and show what our uncertainty is in this region. You know, you wouldn't want to combine this, wind up with 350 ppm, and then somebody says, oh, well, wait a minute. You know, some of your proxies say it was like 200 ppm, glacial conditions. So I don't know these days of any of the you know, kind of a summary. This is the best one that I could find. It comes out of the Yale group. And, you know, unfortunately, we lost a tremendous scientist earlier this year, or actually late last year, Mark Pagani, if any of you know, at Yale, who was very, very active in reconstructing atmospheric CO2 and the geologic record. So he passed away in November. He was very young. He was, I think he was in the late 40s. So it was really a loss to the community. But anyway, let me just finish this up. I said we have this CO2 record. Okay, how do you tell somebody without any question, okay, that this last 150 years is due to human activity? Okay, I'm preaching to the choir here. What's the delta C13 look like on this? Okay, what should the delta C13 of atmospheric CO2 look like? Huh? Which way should it go? If it's due to fossil fuel burning. Okay, you're burning fossil fuel, you're burning plants. Okay, doesn't take much to say the delta C13 should drop. All right. How much did it drop? Well, we have wonderful records on this. Probably the best that I've seen is a record that was collected from sclera sponges from the Caribbean. These are these calcifying sponges that add about 200 microns of skeleton material a year. They're a much better record than corals. And here you're looking at a 650-year record from a single sclera sponge. Starting in 1350 AD, you can see that there's very, very little change in the delta C13 of the skeleton until you hit about 1830, 1840, where we start to drop off precipitously. This is a sponge that lives probably in the upper 100 meters of the water column. The water is capturing the delta C13 of the atmosphere because of equilibration in that upper 100 meters in the mixed layer zone. This is this plot I've been able to find showing atmospheric CO2, okay, since 1000 AD, and you can pretty much see the delta C. This is a sclera sponge record. You see where we are, about minus 8.5 right now? Put this in perspective. This is from the ice core record. This is a great effort by the ice core community to get the delta C13 of the CO2 in the ice cores from Antarctica. And you can see that here's glacial times. We had values of about minus 6.3. We have this big dip in here. This is the deglaciation where we're reorganizing deep ocean circulation. A lot of upwelling of CO2 out of the deep ocean, so atmospheric CO2 could rise. Minus 6.7 per mil. That's where we are today. 8.5. Minus 8.5. There is no way to get there from here because if you look at volcanoes, the CO2 coming out of volcanoes is minus 3 to minus 5. There is no other source on the planet that can move the delta C13 of CO2 in a negative direction, okay, except organic matter. And the argument that, well, couldn't it be deforestation and cutting down and burning trees and wood, that argument goes out the window when you consider the last millennia through the Little Ice Age where the variability is negligible. And that's because when you cut down forests and you burn the wood, all you're doing is keeping that carbon in the fast cycle box. Okay? Stuff that you're burning gets picked up by plants, all right, gets picked up by the ocean, it's recycled, so you see very, very little change in the delta C13 of that carbon, of the CO2. You have to add CO2 to the system that has a very low delta C13 value in order to make the delta C13 drop the way it does. That's why it has to be human activity. Okay, so I think this is the last slide. This is another one that's really good to keep an eye on. This is the rate of change, and it's been accelerating. Okay, so right now we're upwards of about 2010, we were probably pushing something at around 2.5 ppm a year. Okay? You don't have to do the math. Okay? Take it out to 2100 times 2.5, and that's assuming it doesn't, I think I did even 2. Okay? You're dealing with CO2 levels now where you go 160, you're dealing almost 570 ppm. Okay? We're getting dangerously close right now to that tipping point where it doesn't really matter much what we do. Okay? We're setting future generations on a path that they can't engineer their way out of this. All right, so I think we're going to take a break here, and for that, we'll come back to something more pleasurable in a second.